In this video, we're going to talk about the main difficulty with recursive descent parsing, a problem known as left recursion. Let's consider a very simple grammar that consists of only one production. S goes to S followed by A. So the recursive descent algorithm for this production is the following. So we just have a function called S1 for the first production of S, and it's going to succeed if the function S succeeds, and then after that succeeds, we see a terminal A in the input stream. And then we have to write a function for the symbol S itself, and since there's only one alternative, there's only one production for S, we don't need to worry about backtracking or anything. So S will succeed exactly when S1 succeeds. There's only one possibility in this case. And now I think you can see the problem. What's going to happen? Well, when we go to parse an input string, we're going to call the function S, which is going to call the function S1. And then what's the function S1 going to do? Well, the very first thing it's going to do is to call the function S again. And as a result, the function S is going to go into an infinite loop, and we're never going to succeed in parsing any input. This will always go into an infinite loop. So the reason that this grammar doesn't behave very well is because it is left recursive. And a left recursive grammar is any grammar that has a non-terminal, where if you start with that non-terminal and you do some non-empty sequence of rewrites, notice the plus there, you have to do more than one rewrite. So if you actually do a sequence of replacements, you get back to a situation where you have the same symbol still in the leftmost position. And you can see that this is not going to be good for parsing. So in the case of this grammar up here, what happens? Well, we have S goes to SA, goes to SAA, goes to SAAA, and so on. And we can always get to a situation where we have a long string of A's and an S on the left end of the string. And if we always have an S on the left end of the string, we can never match any input, because the only way we match input is if the first thing we generate is a terminal symbol. But if the first thing is always a non-terminal, we will never make any progress. And it just doesn't work. I mean, recursive descent does not work with left recursive grammars. Well, this seems like a major problem with recursive descent parsing. And it is a problem, but as we'll see shortly, it's really not so major. So let's consider a left recursive grammar of a slightly more general form. So here we have two productions now for S. S goes to S followed by something alpha, or it goes to something else that doesn't mention S, and let's call that beta. And if you think about the language that this generates, it's going to generate all strings that start with a beta and are then followed by any number of alphas. But it does it in a very particular way. So if I write out a derivation here where I use a few, where I use the first production a few times, you can see what's going on. So I get S goes to S followed by alpha, and then S goes to S followed by alpha alpha, and then S goes to S followed by alpha alpha alpha. And if I repeat this, I get S followed by any number of alphas, and then in one more step, I can put in beta, and I get beta followed by any number of alphas. So that's the proof that it generates that language, that's the language that begins with a beta and then has some sequence of alphas. But you can see that it does it right to left. It produces the right end of the string first, and in fact, the very last thing it produces is the first thing that appears in the input. And that's why it doesn't work with recursive descent parsing, because recursive descent parsing wants to see the first part of the input first and then work left to right. And this grammar is built to produce the string right to left. And therein lies the idea that allows us to fix the problem. So we can generate exactly the same language producing the strings from left to right instead of right to left. And the way we do that is to replace left recursion by right recursion. And this requires us to add one more symbol, in this case, to the grammar. So instead of having S go to something involving S on the left, we'll have S go to beta. So it produces the first thing, notice, in the very first position. And then it goes to S prime. And what does S prime do? Well, S prime produces what you would expect, a sequence of alphas, and it could be the empty sequence. And if you write out an example derivation here, we'll have S goes to beta S prime, which goes to, now using the rules for S prime, goes to beta alpha S prime, goes to beta alpha alpha S prime, goes to, and after any number of rewrites, we get beta followed by some sequence of alphas followed by S prime. And then in one more step, we use the epsilon rule here, and we wind up with beta followed by some number of alphas. And so you can see it generates exactly the same string as the first grammar, but it does so in a right recursive way instead of a left recursive way. So in general, we may have many productions, some of which are left recursive and some of which are not. And the language produced by this particular form of grammar here is going to be all the strings that are derived from S that start with one of the betas, so one of the things here that doesn't involve S, and then it continues with 0 or more instances of the alphas. And we can do exactly the same trick. This is just generalizing the idea that we had before, where we only had one beta and one alpha, to many betas and many alphas. And so the general form of rewriting this left recursive grammar in using right recursion is given here. So here, each of the betas appears as an alternative in the first position. We only need one additional symbol S prime, and then the S prime rules take care of generating any sequence of the alpha i's. Now, it turns out that that isn't the most general form of left recursion. There are even other ways to encode left recursion in a grammar, and here's another way that's important. So we may have a grammar where nothing is obviously left recursive. So if you look here, you see that the S doesn't even appear on the right-hand side here. And if you look at this production here, A doesn't appear anywhere on the right-hand side. So there's no what's called immediate left recursion in this grammar. But on the other hand, there is left recursion because S goes to A alpha, and then A can go to S beta. And so there we have, in 2 steps, produce another string with S at the left end. And so this is still a left recursive grammar. We just delayed it by inserting other non-terminals at the leftmost position before we got back to S. So this left recursion can also be eliminated. In fact, this can be eliminated automatically. It doesn't even require human intervention. And if you look at any of the textbooks, particularly in the Dragon book, you'll find algorithms for doing that.